In this video, we're going to look a little bit closer at model complexity, and specifically we'll look at the definition of VC dimension. The video will be structured as follows. I'll start by reviewing the form of the bound I showed you in the last video. Then I'll go into the definition of VC dimension and show you how VC dimension plays a role in large margin classifiers like SVM. And before we get into it, I think I just wanted to add that the purpose of these short lectures is not to go through formal proofs of these learning theoretic analyses, but to give you an idea of where their role is in the whole picture of machine learning. So in that spirit, we won't go into the proofs of any of the things I'm going to discuss here. I showed you the bounds from the last video and I didn't prove them. But what you should take away is that somebody has done these proofs, and that if you want to spend enough time and drink enough coffee, you can read through the proofs yourself and see how they work from the assumptions to the result, which usually ends up being this probabilistic bound. So the bound we saw in the last slides took the form as follows. It was bounding the difference between the true risk and the empirical risk. So the difference between the actual error we want to minimize and the error that we're actually able to measure, the empirical risk. And they're bounded, or the empirical risk is bounded from the true risk by some term here underneath the square root, where this term represents the generalization error bound. And the terms in here that are especially important are the VC of H, or the Vapnik-Chervonenkis dimension of the hypothesis class H, the size of the training data, and then some failure probability. So we can look closer at this bound and think about how this is shaped. And if we just look only at the error term, so again, remember the error term bounds the difference between the true risk and the empirical risk. So if we look closer at this, and we can throw away some of these log terms, and we can assume that the delta is constant, so that's not really something we have to worry about too much, then we end up with a term that looks kind of like the square root of some complexity of the hypothesis class over n. And that complexity is actually measured in this case by VC times log of VC, but again, we can drop the log term, so it's basically just the VC dimension of the hypothesis class. So this gives us an idea of what this bound is telling us. It's telling us that if the complexity is fixed, then our generalization error is going to shrink at a rate that's something like square root of 1 over n. Right, and that looks like this curve I've drawn here. So you can see it very quickly drops small, and then it sort of takes a while to get even smaller. And then if we are worried about that log term, this is what it would look like with a log n in there. So this is the square root of log n over n, and it's roughly the same shape. Obviously, the log n makes some difference, but in many settings, especially if n gets much larger than this, it becomes negligible. So that's all good news if our complexity of our hypothesis class is fixed. And you can sort of argue that this is the case for any parametric model, but at the same time, even if complexity is fixed, if it's large and constant, that can be bad too. But now the worst case scenario, or an even worse scenario than if the complexity is fixed, is if the complexity grows with your data. And this happens with non-parametric models all the time. And if the complexity is linear in n, then our generalization bound is going to look like something like square root of n over n, which is just a constant. And that's not good. That means that as you get more data, you don't ever reduce that generalization bound. And we may be getting worse and worse estimates of our empirical risk, or rather our empirical risk becomes a worse and worse estimate of the true risk. So in general, the argument is that we want to make the complexity small to minimize the difference between, or the bounded difference between, the true risk and the empirical risk. So going back to the original bound, before we simplified things, this measure of complexity is done through this VC dimension. So what is it? What is a VC dimension? So This is from seminal research by Vapnik and Chervonenkis that led to the SVM, but started with this type of analysis. And the idea is that the VC dimension is one of many measures that characterize the expressive power or capacity of a hypothesis class. So there's a few words to unpack here. So for a hypothesis class is a class of predictors. So for example, one possible class is linear classifiers in d-dimensional space. That's one type of hypothesis class. Another type would be degree k polynomial classifiers. And you can probably guess, which of these is going to have higher capacity. I mean, it's fairly obvious because a degree k polynomial classifier subsumes all, well, if it's d-dimensional, it subsumes all linear classifiers in d-dimensional space. And then further complex is the hypothesis class of hierarchical axis parallel classifiers, which is what we saw with decision trees. And we can go on and imagine lots of different ways to characterize classes of hypotheses. And once you have the hypothesis class defined, the VC dimension is going to be measured by the ability of the hypothesis class to shatter endpoints. So let's talk about what it means to shatter endpoints. So the idea of shattering endpoints is to classify points into all possible labels. And it's usually easiest to think about this in terms of a binary classification, though there is an analog in multiclass. So if in this example, if we have 2 points, the 2 blue dots are our 2 points. In order to shatter these 2 points, we have to be able to label them in all possible ways, which is going to be plus plus, plus minus, minus plus, and minus minus. So we can see that if we have a hyperplane that I've drawn here, in the little black line with the normal vector attached to it, everything in the direction of the normal vector is going to be positively classified, and everything behind it is going to be negatively classified. So in this case, this classification would give us plus plus, so we can classify it with plus plus. If we move the line a little bit to the right, we can get a minus plus classification, and if we move it all the way to the right, we get a minus minus classification. And then finally, if we flip it around and stick it back in the middle, we get a plus minus classification. So by exhaustively trying members of the two-dimensional linear classifier hypothesis class, we've shown that 2 points can be shattered by that class. 2 points can be shattered by 2D linear classifiers. So now let's try this with 3 points. So what happens if we have 3 points? So again, these are the possible labelings we want to be able to produce with a linear classifier to show that show that linear classifiers can shatter 3 points. And we want to show plus plus plus, plus plus minus, and so on, all the way to minus minus minus. And again, first thing we do is we can classify all the points as positive, and we can also classify all the points as negative very easily, so those are easy to check off. And now if we want to do plus plus minus, we can just move the classifier a little to the left, or the decision boundary a little to the left. We can also continue moving it to the left and get the minus plus plus configuration. And we can rotate the decision boundary to get a plus minus plus. We can rotate it again and get plus minus minus. Rotate it one more time and get minus plus minus. So again, we've been able to shatter 3 points with a 2D linear classifier. So we can continue this exercise, but I can tell you right away that when you go to 4 points, they cannot be shattered by a 2D linear classifier. No matter how you arrange them, there's always some labeling that can't be produced by a single linear classifier. And here's an example one. We've seen this this is basically the continuous representation of the XOR function, and that can't be classified by a 2D linear classifier. So with those examples, you now have some basic idea of what shattering means, and the VC dimension is then defined for any hypothesis class H as the maximum number of examples that can be shattered by H. And this is with a few ground rules. One is that the examples can be arranged, or the feature values of the points can be arranged in any way but then they must be able to be shattered in the same arrangement, right? So you have to align all, you have to set the points, and then you have to be able to label those points that you set in all possible ways. And in general, from the examples that we saw previously, you can generalize that to multiple dimensions, not just two, and figure out that a linear classifier always has VC dimension d plus 1. And that's kind of an interesting exercise to go through, so I'll leave that for you to think about. So why is the linear classifier, or why does a linear classifier have a VC dimension d plus 1? Or not so much why, but can you convince yourself that that's true? So other ways to think about VC dimension and model capacity, you can think of the VC dimension as how many points this model class can memorize, right? Because if you can shatter the points, then you can produce any labeling, and therefore whatever data set you give it that is underneath that VC dimension bound, a learning algorithm that chooses a member of the hypothesis class can choose some hypothesis that will produce any possible labeling. So this is not good because, well, it's good in some ways because we want the model class to be rich enough, or the hypothesis class to be rich enough to represent the different functions that we might be interested in modeling. But if there's some noisy labeling or some mistakes in the data, this is just going to straight up memorize that. It won't do anything like smoothing because it's just going to take the labels that were given and just create a function that outputs exactly those labels. So another view of this VC dimension idea is to think of it as a game, right? So you can think of it as a game, and the game is where we choose a placement of points, and an adversary chooses a labeling. Then it's our task to use our hypothesis class to classify the labeling. So can we pick a member of our hypothesis class that classifies the labeling the adversary gave us, and we got to choose where the points live in our d-dimensional space, but the adversary chooses the labeling that we have to mimic. So this is just another view of the same definition, but it might be helpful to think about it a different way. And then a third view is to think of the learning algorithm as a function that maps from the space of all possible data set inputs. So I'm writing that as calligraphy X, to the space of all possible hypotheses. So A takes some data set as input and outputs a hypothesis, and the hypothesis is a function that maps from inputs to outputs, or the inputs to the labels. And you can think of the VC dimension, or the situation where your VC dimension is equal to the size of Y, or the size of the number of data points, to mean that your learning algorithm can output an H that can output any Y. So hopefully these three different views help you hone in on a way to think about VC dimension. So bringing this all back now to a type of model that we studied, let's think about linear classifiers with margins. So we'll start with an assumption, which is that all of the data that we're going to see lives in some ball of radius r. Okay, so this is a bound on the magnitude of the vectors, the feature vectors describing all the data points. And we can get rid of the radius now. So everything has to live inside this ball. So here's some example points we might draw, and it doesn't really matter where I draw them. And you can recall the arguments we made before about linear classifiers on this 2D ball are the same. So we can shatter these 3 points with linear classifiers. But remember, the argument behind SVM was that we're going to make it actually harder to classify points by requiring that they're classified by a margin. So they have to be classified essentially by a really thick linear classifier. And when we think about how many points you can put inside a radius r ball that can be separated by some margin of width, let's say gamma, which I think that was the term we used before, it brings up arguments about these spatial analysis arguments about packing points into a sphere. So how many points can you pack into a sphere that are some gamma distance apart from each other? and skipping a ton, a bunch of math, we end up with a bound that looks like this, so that the VC dimension ends up being bounded by r squared, so the radius of the ball squared, times W transpose W, which remember was related to the margin when we analyzed the SVM inequality. So again, let's just take this on faith for now. If you want, you can study the analysis yourself. But if we take it on faith, we can look at just this bound. Look at this equation for VC dimension. And you'll note that the one thing that's really important to note is that it doesn't depend on the dimensionality. Right? Of course, there's an implicit dimensionality requirement in that the norm of W, or the squared norm of W, W transpose W, is probably going to, in many cases, going to roughly scale with dimension, but that's not necessarily the case, right? It doesn't have to. And the radius of the ball also probably implicitly does scale with dimensionality, but again, that also doesn't have to. We could imagine a situation where, when we do the RBF kernel, we're working with infinite dimensionality, but presumably the feature vectors in that space are bounded, and similarly the norm of our weights will be bounded. So this is really good news. This is now, we don't have this problem where as dimensionality grows, we have this huge VC dimension that's going to be making our bound really loose. Instead, we can look at this margin-based bound, and assuming that our SVM optimization is doing a good job of minimizing this norm, we'll also be getting smaller VC dimension values. And of course, like I said, we're skipping lots and lots of details, so this is just to give you an idea of the trend here. And I'd like to just summarize and try to put this all in context. So first to summarize, from the analysis, SVM appears to minimize VC dimension, but that's not exactly what's going on, and it's not really correct because, well, it is correct. This is true, right? SVM does seem to minimize, or does minimize, the VC dimension, but the bound that I showed you assumes that the VC dimension is fixed. So there's an alternative bound that does allow for the VC dimension to be a variable, and it roughly has the same shape. So we won't go through that in the same way that we're not really focusing on the actual bound. We're just interested in the trend that it describes. But now, popping back up a level of abstraction, generalization bounds tend to be loose for real data sizes. What I showed you before, the plot I showed you at the beginning of the video, was approximately what the bound would look like if VC dimension was 1, but VC dimension of 1 is absurd. That would mean that all you can do is classify one point, or rather shatter one point. In practice, VC dimension tends to be fairly large, therefore making the bounds large enough that a lot of times they don't even tell you anything because the bounds are bigger than the error could possibly be, in which case the bound becomes vacuous. So that's not good, but of course n is in that bound, so as n goes toward infinity, it does eventually become meaningful, but maybe it has to become so large that we would never have data sizes that big. And this was a major concern, maybe a decade ago or so when people were analyzing these bounds. Now it's less of a concern because we do have really large data sets, but it's still a concern because, right, it opens up a question, right? It formally describes some trend in how effectively learning algorithms can learn or how well they can generalize, but are they useful if they require the n values to be huge? Now, of course, there are tighter bounds. I'm showing you some of the classical bounds where there's been a lot of progress since then that produced tighter bounds, usually requiring stricter assumptions or more sophisticated, or maybe that's not the right word, but different measures of model complexity. And once we have tighter analyses, they do become useful quicker, right? They don't require huge numbers to become useful. But then also the loose bounds, the bounds that do require n to be really, really huge to become meaningful, they still help us formally understand the properties of learning algorithms. So I argue that they still are useful, even if they are loose at realistic settings of n. In the same way that asymptotic analysis of worst case computational complexity is also useful, even if constant factor situations often play a much bigger role in practice because we have much smaller data sizes than the asymptotic analysis shows. But if I can attempt to characterize a debate that goes on a lot in the development of machine learning algorithms, one view is that we should be producing these generalization bounds, and we should be producing algorithms based on known or new generalization bounds, because these bounds give us principles on which we can build algorithms or learning approaches. And the other argument is that the other side of the argument is that, well, these bounds are usually not useful at the real data sizes that we have, so why should we bother with them? Instead, we should just try to come up with cool models and see if they work on real data. And it's an open debate. It's actually hard to tell who or which side is more correct in this situation. But I don't think there's any argument that the best situation is if you can produce both a formal theoretical analysis and an algorithm that works well in practice.